Hello everyone. I'm an undergraduate at the University of Toronto, and today I'm going to present our evaluation and a case study on two Rocq projects. So first of all, what is software verification? I mean, we're here at ICFP, probably all of us are familiar with it, but I still wanted to include some primer on how software verification goes. So software verification can prove the absence of bugs. Successful examples include CompCert, SCL4 microkernel, and many more. And how does it work? Well, you take a specification, such as this function should always return a sorted list. You take a program, and then you write a proof using either proof assistants, such as Rocq, Lean, Agda, or you help guide a proof assistant using automated theorem provers, and sometimes called autoactive theorem provers, such as Daphne, Varus, Y3, and many more. And then if the proof assistant does not give you any errors, then you say that your program obeys your specification. So your program should at least be correct. And as an example, this is the Rocq proof assistant, which we evaluated our case study on. So this is a definition of a stack. You can push, you can pop. The exact syntax does not matter right now, but what matters is the fact that Rocq has a small trusted computing base where you can write proofs, and if your proof passes the check, then it means it's 100% correct. And this is an example theorem where if you push something and then pop it, you get the exact same results back again from the stack. And you can see that QED is right now underlined because we haven't written a proof. And then at the right-hand side of your IDE or text editor, you can see this proof goal. And then as you write some tactics, which is basically writing your proof, you will see that your QED line will disappear if you successfully complete the proof. Okay, so what's the problem with software verification? Well, verification is costly, and most of the programmers like to code, but they don't like to test or prove. I mean, can you blame them? Sometimes this is an example proof from Verdi. Yeah, you can imagine how long these code bases can get. The question is, can the LLMs usually automate proof writing? And particularly, if they can, what kind of context do they need about the code base? And because we have a context limit in the LLMs, we can't just copy and paste the entire code base into it because the LLM will forget and its performance will reduce and so on. And yeah, of course, another bottleneck is the price. Even if you could, hypothetically speaking, put your entire code base onto the LLM. And how can you make your code base LLM friendly if you just want to prove it? And do you want smaller proofs? Do you want everything in the same file? Do you want things in different files? How do you want it to go? And how does your code base affect the LLM's proof writing performance? And most importantly, how are the qualities of proofs generated by LLMs? So, I mean, they can pass the proof checks in Rocq, but how are they? Like, are they smarter, like more elegant than maybe human proofs? Well, we are going to attempt answering all of the questions. So for our study, we picked two Rocq projects. The first one is Verdi, a framework for implementing and verifying distributed systems. It has around 579 proofs, and just to give you an idea of the size, 19% of the proofs have 25 plus tactics, and majority of the proofs in Verdi has around 5 to 9 tactics. I will introduce the exact numbers later. And for another project that we picked was hs-to-coq, the base library of hs-to-coq. It translates a subset of Haskell to Rocq so that you can reason about your Haskell programs. It has 187 proofs, and 5% of the proofs in there has 20 plus tactics, and majority has around 0 to 4 tactics. And just as a note, both have relatively old Rocq versions, 8.11 and 8.10.2 respectively. So how do we answer our questions? Well, first of all, we have this notion of dependencies, and we extract the dependency for each proof. So a dependency is any signature that the original proof relies on, including definitions and theorems from any other source file, including lemmas, notations, records, definitions, and so on. In the stack example, this is push, pop, and the stack definition itself. Another concept we have is the lines before that come in the file. So for a file, all lines that come before where the given proof begins are also given to the LLM in this ablation. So this works because Rocq doesn't really scan ahead, so you can't really hoist the proof, and you have to refer to definitions you have written before and theorems you have written before. And we define success as if you can write QED at the end of the file without using any assumptions or cheats, basically like admitted. Okay. So we also have 4 different evaluations. So we have full context informed. So this mode includes both external, which is other file dependencies, and all of the previous lines in the file of the proof. Another evaluation we have is no external dependencies or notations, but this one includes all of the lines that come before in the file. The third evaluation is without in-file context, which still includes the same file dependencies. So even if you have different dependencies in your current file, we include them as long as they're in the same file, even though we're in the in-file context. And for the fourth one, we have no context provided at all. So we just give the LLM the proof and the signature, and we ask the LLM to complete the proof. And we evaluate on GPT-4o Mini, GPT-4o, O4 Mini, DeepSeek Prover v2, DeepSeek R1. And O4 Mini and DeepSeek R1 are reasoning models for context. And DeepSeek Prover v2 is trained with lean proofs, just in case you don't know. And DeepSeek Prover, well, we're including DeepSeek Prover v2 because we're interested in whether it has learned from writing lean proofs or being trained on lean proofs, and whether it can also work on Rocq as well. So what are all of the results like? Well, these are the results in short. I mean, I'm not going to just let you look at those. I have a few takeaways, but overall, you can see that for hs-to-coq, which has around 187 theorems, we can get around up to 51 to 52% accuracy with the best model, whereas with Verdi, you can get around 30% accuracy with the best models. Okay, so what are the takeaways you can have from this table and moreover from our study? And just an important note for this table is that this does not involve any feedback loop, so we just gave all of the proofs once, and we did not give the LLMs any feedback at all. So this is just calling the LLM once. Okay, so what are the takeaways? Well, models perform the best with more examples in terms of Rocq syntax. We all know models perform best with examples usually, but one interesting thing is that models don't really properly know Rocq syntax, first of all, because there are usually many syntax errors that we have figured out in our examples, in our evaluation, and many syntax errors that were caused by the compilation process. And when we give the lines before, even if the lines that come before in the file are not necessarily related, the model seems to at least learn the syntax a little bit, which is surprising considering large language models should know the syntax, at least get it right. Another takeaway is that context retrieval is crucial for automated proving, and the largest drops in success rate occur when the information is omitted. And this is another point where you have to be careful about what you provide to the LLM because of the price. So here we have included a token count for each ablation. For example, if you just include everything in the code base, then it can go up to like 3,300 tokens for one proof. Or in Verdi, it can go up to 7,000. So it is going to get really expensive very quickly. And another question we had was, do LLMs really copy the answers? As in, do they really generate the exact same proof that was present in the repository, including like we just do an equality check, string equals equals. Here in this graph, you can see the exact same figures, exact same proofs highlighted in dark, and then the original success rates in lighter colors. And in the x-axis, you can see the interval ranges. So for 0 to 4 proofs, you can see that the LLMs have kind of copied the proof, but it doesn't really mean anything as much in this case, because 0 to 4 tactics, you can pretty much have an identical proof by coincidence. And this is for hs-to-coq. And another takeaway here is that LLMs perform better on small proof sizes, but I would just want to show you Verdi right now, which you can see that still for lower number of tactics, the LLMs have kind of generated the exact same proof, which is expected, but it has also generated exact same proofs in longer tactics like 20 to 24, or or proofs involving 15 to 19 tactics. Yeah. Another takeaway is that the impact of adding or omitting information depends on your project structure. So, for example, one really interesting thing is for hs-to-coq, if you add more context, it actually decreases the success rate. And for example, this graph shows how much percentage you lose from going from just dependencies only to including the previous lines in the file, which are not always necessarily related. So in this case, you can see that for larger proofs like 15 to 19 or 20 plus, it just causes the model to get confused. So again, do not give the entire repository like you would with just copying and pasting to ChatGPT or something else. Okay, so another thing is we want to ask how is the quality of proofs generated by LLMs? Like, are they elegant, or are they like maybe shorter than human proofs? Okay, so in our first example, this is an example from hs-to-coq, and I mean, I'm not. This is quite hard to read, so I'm just going to give a summary. Well, in this case, in this proof, what we're doing is we're doing a case analysis on the equals operator, which gives you two cases when the equals operator, let's say x1 equals to x2, is true, and the case when x1 is equal to x2 is false. And this is the original human proof that was found in hs-to-coq, and this is a proof generated by DeepSeek R1. And what is really surprising about this is not the fact that it's just shorter, but the fact that it has chosen to do the case analysis on propositional equality, so x1 equals to x2, rather than x1 equals x2. So it is taking a different approach, and again, the LLM doesn't really know the original proof. We did not give the proof to the LLM. It's just taking a different approach, and it's just making the proof kind of smarter in this case, and this was really surprising to us. Another really simple example is from hs-to-coq again. Here you can see that we're just introducing the variable, destructing variable, and then calling auto over and over. So you can the LLM just realizes this. Again, it does not have the proof, but it just figures it out on its own. It says, okay, I can just chain the tactics together using semicolons, and then I can just complete this proof really quick, like this. And another thing, and another interesting example comes from Verdi, where the proof is quite long. There's like around 29 lines in this proof. But I mean, the proof, how long the proof is, does not really matter in this case. But what is important is the fact that Verdi developers, choose to copy paste, which is okay. But then the LLMs, in this case, O4 Mini, realized that this existing lemma is a contrapositive of another a theorem that already existed in the code base. So it was able to figure that out because we included all of the previous lines in this case. And it was able to figure that out, which, using contrapositive is quite good. And there are also cases where the LLMs are not necessarily doing well. We set the temperature to 0.1. So we hypothesized that this might have caused the LLM to just repeat a few things. Like, for example, it just gets stuck at rewriting a quality operator, just goes on by repeating the rewrite. And yeah, so there are some cases where the LLMs still get stuck. And to conclude, LLMs can be good at proof generation, but you have to give them the right context, and context retrieval is important. LLMs can work better with small proofs, but they can also do larger proofs, but they still can output small things and still get the proof right. And the larger proofs the LLMs write can be shorter, but this is surprising because they're not shorter for one reason, they're shorter for various reasons. If you're interested in a more detailed explanation, you can also read the paper. And if you're interested in what future work you can do in this area, is that one really important thing here is that we need more software verification benchmarks, especially for Rocq and its latest versions, because hs-to-coq and Verdi are in versions 8.11 and 8.10. So an updated benchmark for Rocq would be quite nice and helpful. And another point to note here is that existing benchmarks of interactive theorem provers mostly focus on math and Lean 4. But previous research actually shows us that software verification can be harder than just writing math proofs. Well, there are two different areas, but if you compare the success rates in latest benchmarks, you can actually see that they're actually quite low and sometimes even less than 10%. And in fact, in some cases, LLMs can also get 0% with some automatic verifiers like Barış, Daphne, Vitri, and so on. Yeah, and there's some recent work in this area includes Verina, Clever, Verified as Benja, and so on. And software verification benchmarks for LLMs, especially software verification benchmark for LLMs, especially Rocq, are underexplored, as I've said. And some other questions: how do LLMs do with refinement in our code base? We were not able to, in our study, we were not able to actually run the experiment with refinement. But if you want to modify our code base, so if you want to, run the experiment in our code base, we actually support refinement in our code base. Just with a really simple change, we extract the error messages as well. And what are some good methods to retrieve context? Should you apply retrieval augmented generation? Should you maybe use another LLM to retrieve context? Or how would Rockhammer context extraction do, or premise selection do in this case? And if you're interested, you can scan the QR code here to read our case study paper. And thank you for listening.
Hi. So if I understand this right, like you took, let's say, hs-to-coq, you kept all the definitions, you kept all the properties, and then you removed all the proofs, and that's what you, But of course, that means that you still, like, if let's say I'm writing hs-to-coq, there's a bunch of properties that I care about, and a lot more that I'm going to add because they're useful lemmas on the way to getting to the thing that I really care about, right? Like lots of invariants, whatever. So my question is, have you tried removing those as well? And because there's a lot of creative work is already being done just by coming up with the right invariants. Like that's also hard work, right? Like ideally by the time you get to the actual thing you want, that's very easy to prove because you've put in all the work of, So is that something that this can be?
You mean removing sorry, could you repeat like the removing part of the question? Like
Imagine that you have one or two key properties. Those are the ones that you actually want to prove about your software, right?
Yeah.
But before that, you have a whole lot of lemmata, right? And a whole lot of invariants and whatever. And if you haven't come up with those yet, then it would be much harder to prove the thing that you eventually care about.
Yeah.
But if you keep all those, you're kind of guiding the LLM down the same path that the human has come up with.
Yeah, well, in this case, because there are a lot of proofs, it is going to, we haven't explored that, but I mean, you could theoretically take them and take the few theorems that you mentioned, or lemmas, or properties, and then omit them and then rerun as well, but we have not done that. But I guess it would be a good idea to explore, because,
Okay, thanks.
Hi, actually our team did a similar job, so we are Copilot team. We're all here, we would be happy to chat. And I have a question regarding data contamination. You ran your benchmark, and how are you sure that LLMs haven't previously seen the proofs for your theorems?
Okay, thank you for the question. So, we can't truly be sure, but this is why we just wanted to check if these two things were equal. But this is not a perfect way to check it, and I don't think there's an easy way to know if it's included in the training data. But since these projects are on GitHub, I think it's safe to assume that they might have been contaminated or be seen by LLMs. But again, I don't think there's a good way to check for it. And another point to mention here is that Verdi is actually in another study called Xujie. So yeah, Verdi was in another benchmark as well. But I agree with you that there might not be, they might have been previously seen.
Okay.
The idea was that if we check maybe for equality to demonstrate it here, maybe we couldn't know, but yeah.
Thank you.